Hello everyone, we are Group 6 and our research project is titled Early Detection of Atrial Fibrillation from ECG Signals Using Deep Learning. I'm Fahad and with me are Animesh and Ahmad. In this video, we'll walk you through our motivation, approach and findings. Let's start with introduction part. Atrial fibrillation is a common cardiac arrhythmia that affects millions globally and increases the risk of serious conditions like stroke and heart failure. Detecting atrial fibrillation early is crucial because interpreting ECG signals accurately requires clinical expertise and is time consuming. With the rise of advanced machine learning and deep learning techniques, we now have an opportunity to automate this detection process. This can significantly reduce human error, speed up diagnosis, and support healthcare systems under pressure. There are many challenges in F detection because this task isn't straightforward. First, arterial fibrillation is often paroxysmal, meaning it can occur unpredictably and go unnoticed. Second, ECG signals are noisy and contain overlapping features between atrial fibrillation and non-atrial fibrillation segments. And finally, the dataset is imbalanced. Atrial fibrillation cases are much fewer than normal ones. This makes models training and generalization challenging. To address this, we explore 2ML models, random forest, which works with handcrafted features, and convolutional neural networks, which learns directly from raw ECG signals. So next, with our model design and implementation, Ahmad will walk you through the dataset and that we used and the models we developed. Thank you.
Okay, so my name is Ahmad, and now I'm going to walk you through dataset, pre-processing, and random forest, and our applied random forest and CNN models. Okay, so the dataset we used was MIT-BIH Atrial Fibrillation Database from the PhysioNet. It includes 25 long-term ECG recordings, each about 10 hours long, collected from patients with paroxysmal AF. The ECGs are sampled at 250 Hz and annotated with rhythms like AFIB, AFL, and normal. This rich annotated dataset made it ideal for training machine learning models focused on early AF detection. Now let's move on to pre-processing pipeline. Our data pipeline began with filtering out noise using a bandpass Butterworth filter. We segmented the ECG into 5-second windows, which corresponds to 1250 samples per window. We then normalized each window using Z-score standardization. For leveling, if a window contained AFIB or AFL annotations, it was marked as AF. Otherwise, it was labeled based on rhythm at the start of the segment. The final dataset was split into training and test sets with stratified patient-level splitting to maintain class balance. Okay, now let's talk about our two applied models. The first one is random forest approach. So first off, we used manually extracted features like RR intervals and heart rate variability. We applied class balancing techniques to improve detection of minority AF segments. The model achieved about 70% accuracy with a macro average F1 score of 0.70 and an AUC of 0.78, showing good overall discrimination between AF and non-AF. Now let's move on to our final model, which is CNN. So here we built a 1D convolutional neural network that learns directly from raw ECG signals, avoiding manual feature extraction. The model had two convolutional layers followed by fully connected layers and dropout for regularization. It achieved a training accuracy of 98%, but the validation accuracy was only 71%, which indicates overfitting. While the CNN showed high recall, which was 0.85 for AF, it struggled with generalization due to complexity of raw ECG patterns and class imbalance. Next up, Animesh Bhattacharjee will finish this video.
Animesh Bhattacharjee. I want to discuss about the research and discussion part of our research project. Um, uh, for the random forest, we achieved almost 70% accuracy and a better AUC of 0.78. It handled the imbalanced data really well and gave stable results. For the CNN, we achieved slightly higher recall for atrial fibrillation but had a lower AUC of 0.67 and signs of overfitting. Overall, both models were effective in different ways. RF worked better on structured features, while CNN actually extracted patterns directly from the raw signal. Um, about the limitations, some challenges remained actually. First, the class imbalanceness affected both models, especially CNN model. Um, Random forest used class weights and CNN used early stopping but more robust methods like SMOTE could be actually implemented, and it would also help do a better project, I guess. For CNN also there is a overfitting issue due to some like simple architecture. Deeper models, data augmentation like jittering or time shifting and better hyperparameter tuning could enhance its performance. For random forest, adding domain specific features could further improve the precision and recall. For conclusion, both the random forest and CNN models showed really strong potential for early atrial fibrillation detection from ECG signals. While random forest offers stability and simplicity, CNN demonstrated the power of learning from raw data. With further improvements, especially around data handling and model complexity, these approaches could make real-life atrial fibrillation detection more accurate and scalable, benefiting both clinical and patients. Thank you.